Good morning and welcome to Argonne National Laboratory's Science at Work webinar series. Today we're going to discuss how electric vehicles compare to conventional vehicles in terms of greenhouse gas emissions. We'll also explain how to track those emissions as well as measure them in other areas of the economy such as plastics, agriculture, and building materials. My name is John Harvey. I'm a business development executive in Argonne Science and Technology Partnerships and Outreach Organization. Just a few logistical notes before we get started. For a better experience, please check that your VPN is disconnected. If you're having trouble with the technology of this webinar, we recommend that you exit and re-enter. As you'll notice, your video and audio were automatically turned off when you joined the webinar. We encourage you to ask questions in the public chat window. Because this event is so short, we will not get a chance to answer those questions during the webinar, but we'll respond to questions via email after it's over. Finally, please note that today's webinar is being recorded and will be made available at a later date. Now I'd like to introduce our speaker for today, Jarod Kelly. Jarod is a principal energy systems analyst in the lab, where he examines energy and transportation systems through an environmental lens. Jarod, we look forward to your remarks.
Thanks so much, John. So my name is Jarod Kelly. I'm a principal energy systems analyst here at Argonne National Labs. And there's a thing I keep getting asked because of the work that I do, which is, which is better for the environment, a gasoline car or this new electric vehicle? Is that electric vehicle actually better for the environment? And, because I'm an analyst, my answer to that is wholly unsatisfying to the people that ask it, because it's always, well, that depends. Because in truth, we have to ask, what does better mean in this context? When we talk about better from an environmental perspective, are we talking about resource depletion? Are we talking about greenhouse gas emissions? Are we talking about other criteria air pollutants such as SOx emissions, particulate matter, NOx emissions, that sort of thing? And then, what are the performance parameters of the electric vehicle that we're considering versus the gasoline vehicle that we're considering? Are we talking about the smallest, EV that we can get on the market versus the largest gasoline vehicle? I think we can all figure out what the sort of answer might be there. Or is it vice versa? Or really, are we comparing apples to apples as best as we can? And then finally, when we consider electric vehicles, we have to think about, where is the electricity coming from? What are the assets that are being used to generate the electricity that the EV is using? So at Argonne National Laboratory, we have the opportunity to examine those questions in a very detailed fashion using what we call the GREET model. GREET stands for, next slide, please, the greenhouse gases, regulated emissions, and energy use in technologies. This framework allows us to do an analysis of the fuel cycle, which you'll see on the horizontal of this diagram here, as well as the vehicle cycle, which you'll see on the vertical. The fuel cycle includes all stages of energy production, from extraction of resources from the earth, through refining, through delivery to an electrical plant, or delivery to a gas station, and then finally, delivery to your vehicle. And the vehicle cycle includes all of the information necessary to consider the production of a vehicle. So the extraction of bauxite, right, that can get converted to alumina, to aluminum, and so on and so forth, with all of the materials that go into vehicles. So with this, we are able to look at all of these stages. And by technologies, we don't just mean vehicles. We do have access to resources for buildings, for a variety of different technologies that are available in the market. So this model, the GREET model, is being used by over 50,000 registered users worldwide, with many users in North America, as well as other parts of the world, including Europe and Asia in predominance. We're also used throughout industry, government, and academia. In fact, the GREET model itself has been utilized in the formation of, or to inform policies. So from the National Highway Traffic Safety Administration, or NHTSA, and the EPA for some of the regulations that they have. It's also informing a model from the California Air Resources Board called California GREET, and they developed their model based on ours. So this model is helping others understand the life cycle of transportation in particular in this case. I noted that we can think about electric vehicles versus gasoline vehicles on a variety of different metrics. The GREET model has applications to energy use, so that can include fossil energy, renewable energy, from a variety of different fossil sources and renewable sources, as well as different air pollutants, including volatile organic compounds, carbon monoxide, NOx, particulate matter of different sizes, SOx. And we have these at both total and urban levels. We also have greenhouse gas emissions, right? And when I say greenhouse gas emissions, that's carbon dioxide plus the other various GHG forcing agents that are out there, including CH4, N2O, black carbon, et cetera. We also allow for the analysis of water consumption. Now, one of the things that I mentioned earlier was that we look at the life cycle of energy production, right? And so that goes through a variety of different stages. And so if we just focus on something like petroleum fuels, as we look at the diagram there, the crude oil production would include everything from the exploration and recovery of that crude oil, through the transportation of the crude, to petroleum refining, fuel transportation and distribution, and finally, fuel combustion. And you can imagine that we have that for coal, we have that for natural gas, oil, as I said, and a variety of other renewables. So we have this for biomass sources as well, so ethanol, et cetera. So all of that is considered within our modeling effort. And then when we start thinking about electric vehicles, most people think right away about the batteries. And that's an important thing to consider. And in fact, the GREET model has a significant battery module in which we have all the materials that go into the cathode active material. So that includes lithium from a variety of different sources. We have nickel, manganese, cobalt, the various, not precursor agents, but the various support agents such as soda ash, lime, hydrochloric acid, sulfuric acid, et cetera, alcohol, whether that be ethanol or methanol. And then we have the same sort of modeling effort for anode materials, the binders, electrolytes, the battery management system, and all of the support structure for the battery. As I noted, lithium can also come from a variety of different sources. That can be brine, it can also be spodumene ore, it can come from Chile, it can come from Australia or other locations. So all of these different components are pieces that we have within the model that allow us to examine this on a very detailed stage. So that really does bring us back to the question that people are here for. You know, what about EVs versus gasoline vehicles? Which is better? You want a simple answer, right? So let me focus on greenhouse gas emissions. Okay, if we focus on greenhouse gas emissions, we can start to talk about better, right? And now, if we're going to talk about two vehicles versus each other, let's consider a common vehicle. Let's consider a mid-sized sedan with equivalent performance conditions, acceleration, maximum speed, et cetera. That information actually is informed to us by a model within Argonne called autonomy, which I would encourage folks to investigate as well. And then finally, when we talk about this issue, let's consider electric vehicles used in the United States using the average US grid mix to start, okay? So if we go to the next slide, we have the answers, right? So this is the life cycle greenhouse gas emissions for gasoline vehicles versus electric vehicles charged from different sources. So the very far left stacked bar is a gasoline mid-size sedan with a 31 miles per gallon gasoline equivalent operations performance. You can see that the EV immediately to the right of that is charged on the US average grid. It is a 300-mile range electric vehicle that has 124 miles per gallon gasoline equivalent. So both of these vehicles are consistent with vehicles available in the market. And we can see that in this case, the electric vehicle significantly outperforms the gasoline vehicle from a greenhouse gas perspective. But what does this mean by different fuel types? We can see that coal still slightly improves upon the gasoline vehicle. We can see that natural gas improves upon the gasoline vehicle. And also, as we would assume, renewable electricity improves upon the gasoline vehicle. How do these coal, natural gas, and renewable assets sort of represent themselves across the grid within the United States? Well, I've prepared a couple different locations, the upper Midwest, Texas, California, and the Northeast, running from left to right. We can see at the upper Midwest, so the Dakotas and that kind of area has a slightly higher greenhouse gas emissions per mile basis than the others, being Texas, California, and the Northeast. Northeast has a significant quantity of electricity from hydropower, representing an improved greenhouse gas performance. The blue portion of the bar represents the vehicle. The yellow portion of the bar represents the battery. And the pink portion of the bars represents upstream. And the tailpipe is represented in the dark red. So the tailpipe is just what's emitted from the tailpipe. Upstream is all of the greenhouse gas emissions associated with all that process of producing the fuel and getting the energy. And the battery, you can see, represents a significant portion of the vehicle greenhouse gas emissions. I believe at this point, we are close to running out of time, and so I will wrap things up. Thank you.
Great, thank you, Jarod. That was a great talk. It looks like we have time for at least one question. So, since I have the mic, I'll get to ask the question. So, in your opinion, what are the biggest causes for concern with respect to the future of EVs?
That's an interesting question. So the future of EVs have a variety of different considerations, right? There's a lot of different resources. So things like lithium, nickel, cobalt, manganese, et cetera, graphite that go into the batteries. So as we increase the number of vehicles on the road, that's going to put a pressure on the extraction of those material resources. So that will influence things. Counter to that, most places within the world are reducing their associated greenhouse gas emissions from electricity. So that will cause an improvement in the performance of those vehicles. I think on balance, that would suggest that we would probably expect to see an improvement overall.
Great, thanks. Thank you again, Jarod, and thanks for the time.
You're welcome. I'm just seeing some of the questions now. This is great.
Again, thank you all for attending the event today. I want to remind you that we will send written answers to the questions you sent via chat, along with a recording of Jarod's talk. If you have any questions or would like to learn more about how to partner with us, please reach out to partners@anl.gov. That concludes our webinar today. Have a great day and enjoy.